Good morning. My name's Kevin Farley. I'm a program manager in the SQL Server product team. I've been in the SQL Server group for about 10 years, so I've seen a lot of evolution of the product. This morning, we're going to step back a little bit and do an overview of the in-memory technologies. There's some confusion with the titling on the programs. This isn't about Azure so much as it is about the on-premise product, although it does apply, as you'll see a little bit later. So this is really all about understanding what the technologies are about. We've seen flashy demos. We've seen how cool this stuff can be. I want you to come away from this with an understanding of what is really going on behind the scenes, what it is that makes these technologies fast, why it matters. Okay. So in recent years, in the last release, the SQL team went deep in a few selected technologies. And a lot of people got really worried about that because they saw certain technologies being invested in. They saw the in-memory technologies going big, not a big surprise there. Some enhancements to high availability, some hybrid scenarios, and not a lot else. And there was a lot of areas of the product that we didn't choose to invest in. And a lot of people got really worried about that because they've seen areas of the product get kind of orphaned and nothing happened to them. That's not what's going on. What's going on is that we're changing our engineering model quite substantially. So instead of just going over and investing in the entire product somewhat thinly and taking however long it took to get all that software engineering up to a level where we could ship it, what we're doing is being more targeted in strategic areas of technology and going deep and going well. The other thing that has changed really dramatically is the engineering processes that we're using behind the scenes. So it used to be the case years and years ago, back in the 2005 days, where we'd open up a release and the engineers would just check in everything that they've been thinking about for the last couple of years. So we'd get all this functionality in and most of it was broken. And we'd spend the next couple of years getting it to a point where we could actually expose it to the public without embarrassing ourselves. So we've pivoted that around to where now we're in a state at this point where the main source tree, SQL main, is always at a state where we could turn around and ship it. What we do is instead of putting in all the functionality early and incrementally adding quality, we've pivoted that to where the quality is always there and we incrementally increase the functionality. So by the time someone checks in and lights up a new feature, it's ship ready. Just as an example of that, one of my other hats is that I run the TAP program, the early adopting program, where customers that want to do a deep engagement on early bits can get exposure to those bits. The goal is for them to put those in production before we RTM with full support. So with those customers, we're actually turning the crank really fast. They get a build, a production-ready build, once a month. That's how fast the internal clock is going. That's not what you get to see, but that's the pace that we're running internally. So that's just kind of a little bit of context about how things have changed in the engineering side of things. So in the last release, we focused on in-memory. We introduced in-memory OLTP and in-memory data warehouse. So those were some pretty cool, or we didn't introduce in-memory data warehouse, but we introduced the clustered column store, which is a major enhancement. We continued investing in always on. We've gotten the message loud and clear that it's really annoying when we roll out a new feature set and kind of set it aside and don't invest in it anymore. We're continuing to invest in features that were new and shiny a few releases ago. We're not letting them just sit there. So that's the case with always on. That continues into SQL Server 2016. We're investing in that technology fairly significantly in 2016. Online database operations. That's about reducing the number of times when you can't get access to your data. So operations that would have taken the database offline for a period are now being made online. We're doing a lot of work in the back end to keep you from losing any encountering any downtime in your applications. Hybrid scenarios is an interesting space where we see that as one of the differentiators of SQL in the market space overall. There's quite a few vendors, as you all know, that work on-premise. They've got in-premise databases that are really good. There's a lot of companies that have a presence in the cloud. You know, the usual suspects are there. There's nobody that spans that whole range, that has credible offerings on both ends and hybrid in the middle. So what we're doing is connecting those two worlds very aggressively. So we've got a bunch of scenarios within SQL Server 2014 where we're starting to invest in things like backup to Azure, where instead of doing your backup locally and sending it off to Iron Mountain or some other vaulting company, now the backup goes directly up to Azure storage, where it's encrypted before it leaves your facility, so it's protected, and we guarantee that it's available up in Azure. So essentially, we're your vaulting company. HA to Azure VM. So how many people have used always-on availability groups? So now you can click through in a wizard, starting with 2014, and at the end of that wizard, we will spin up a new VM up in Azure and join it to your availability group, so you can have a remote data center. It's quite attractive for some companies that are a little bit too small to have a dedicated DR site. We're your DR site without having to staff a whole new building. We're working very closely with the Windows Server team, so I was in a sync meeting just last week, just making sure that the two organizations are in sync. We're aware of what each other is doing and able to leverage the new technologies. For the last release, we announced support for the new REFS file system, a bunch of work in Hyper-V area. So that's just to say there's a lot of different investments going on in a lot of different areas. That's the package that came out in SQL Server 2014. What I'm going to focus in on this talk is the in-memory OLTP and in-memory data warehouse. In-memory OLTP, as the name suggests, is applicable to transactional workloads. So your typical order entry, similar sorts of systems. The characteristics are that there are a lot of concurrent updates of the data. Accesses tend to be targeted at one or a small number of rows at a time, as opposed to the data warehouse, which is more applicable to decision support workloads where you're doing aggregations across broad swaths of data. And those are two very different patterns as far as the database is concerned. And so these technologies target very specifically those two technologies. So just kind of the outline of what I'm going to talk about. I'm going to give an overview of the in-memory OLTP feature. Talk about motivating trends. Why did we do this work? Why did we think this was a good idea in the starting place, right? How many people have been to a talk like this where you get the basics of it? Okay, excellent. We're going to talk about the architecture of in-memory OLTP, what happens under the covers, what are we doing, why is it fast, what makes it quick? And it's the hint here is it's not because it's in memory. So I'll leave that hanging and let you think about that. We'll give you some real-world performance and customer results. We had over 20 customers live in production before we shipped SQL Server 2014. And some of them got some pretty interesting results. And we're going to talk a bit about what's new in SQL Server 2016. There's a session this afternoon at 5 down in 105 where I'll go into a lot more detail into what's coming in SQL Server 2016. In-memory data warehousing overview is, again, just talking about what is this column store thing? How does that really work? Why does it make me able to handle much bigger pieces of data than I was in the past? So what's that all about? Go into that. What are the benefits? How does it work? And again, a teaser about what's new in SQL Server 2016. Sunil has a session on operational analytics, which is a big piece of that this afternoon. So why did we do in-memory OLTP? Hekaton was the code name the engineers used while we were developing the feature. We're typically in development for a year or two before marketing decides what they're going to call it formally. We have to call it something. So Hekaton is the Greek word for 100, and our sort of aspirational goal was 100 times faster. In some cases, we hit that, but that's not the main line. So why did we start looking at that? It was an early development project, started out as, and we saw several things. There's some observations we made in the marketplace as to what people are doing with databases in general, and also some observations in the technology space that we thought changed the game a bit. In the customer space, we saw that there is a demand for always higher throughput, higher performance OLTP at a lower cost. The extreme example, of course, would be trading systems where you have extreme requirements for latency and throughput. A lot of other examples we'll get into as we talk to customer stories. That picture there is just an example of an extreme latency scenario. It's not something we're playing in, but just an example of the need out there. And that green line is actually a laser link between two trading systems. And they're using that to get direct line of sight to reduce the latency of the communications between those sites, because milliseconds matter in those sorts of technologies. The other example I like to quote is that in a lot of the trading systems, the rack space where they host computers is priced differentially based on the number of feet it is from the main trading computer, because the number of feet it is changes the latency. So we're not able to play in quite that nanosecond range yet, but that's sort of the environment that we saw in the marketplace that drove our thinking as to why should we do this stuff. Hardware trends, we noticed a couple things. We noticed some trends in the CPU space as well as in the memory space. That chart there is one I like. It's really interesting. Each of those dots actually represents an Intel processor family. So this is real data. Took a long time to research that chart. The green line is the number of transistors per chip. And that's illustrating that Moore's law continues. So Moore's law says the number of transistors per chip doubles every few years. And that holds. This is a logarithmic scale, so it holds. Chips are getting more and more complex every year. But the next line down is really interesting, and that kind of took us by surprise. Not new news to anybody in the room if you've been thinking about it, but the CPU clock rate hasn't really changed in quite a while, right? We're running 3 gigahertz plus or minus, right, for a good 10 years or so. If you look farther back on that chart, you remember that it used to be the case that every generation of processors, the clock ran faster. So even if you're running a single-threaded app, just by running on the new processors, it's going to go faster. That's no longer the case. You can't get a faster execution just by running single-threaded on a new generation of processors. They may have a few new instruction sets that help, but in general, they're not going to run faster just because it's the next version. The bottom line is about power, because one of the things that's capping the clock speed is that due to the physics of really high frequencies and short wires, the processors would melt if you go much over 3 gigahertz. It's a combination of them melting and turning all those signals into radio waves. The point here is we're getting more and more complexity in each generation of processors as we go along, but we're not getting it in terms of faster clock speed. So how do you get the extra power out of the new generations of processors? We're getting it, obviously, in the form of more and more cores per socket. So in order to get the benefit from these new generations of processors, you have to be able to use all those cores. How many people were in the last session in this room? So one of the demonstrations that Lindsay did was a live demonstration of an HP Superdome with 64 cores running on it live and taking advantage of all those cores. That's a highly optimized workload that takes advantage of all of those threads of execution. If you've got software written decades ago that only uses one thread of execution, you're only going to use one of those cores, and the rest of them are going to be idling, burning electrons. So in order to get advantage of all of those cores that you're paying for, you have to have a workload that can efficiently run multiple threads a lot more highly parallelized than was the case in the past. And you have to do so in a way that those threads don't interfere with each other, especially in a database environment. It's really easy to get into a situation where you're trying to do a whole lot of work at once in a database, and all those threads are blocking each other, right? So you end up all the threads sitting behind lock weights. So that was something we observed in the hardware space. The other issue was the price of PC memory is dropping. That's not new, right? Since there's been memory in computers, it's been getting cheaper year over year. But there's been a qualitative shift in how much memory you can get in a commodity box. Generally, it has been the case that the workspace, the size of the data set that you would typically use in an OLTP system is much, much larger, orders of magnitude larger than you could think about having memory in a system. It's not the case anymore. And the illustration I like to use is a system that I spec'd and purchased for the development team to use in perf studies as well as some demos. It's a commodity box. It's 2-socket, 256 gigs of main memory, 4 SSDs, and a bunch of spinning drives for bulk storage. And that was about a $13,000 machine. The point is, at a commodity price point, and that was several years ago, but the point is, at a commodity price point, you can now get a really interesting amount of memory. A lot of whole work sets will fit in 256 gigs or less. So if you can potentially have most or all of the data you care about from a performance standpoint sitting in memory, maybe we can do things differently. So that's where the Hackathon in-memory OLTP project came from, is thinking about all those things and synthesizing them. So we think about in-memory OLTP in terms of these 4 pillars. Is the way I really like to think about it. The first pillar is based on the observation that performance-critical data fits in memory. So this doesn't mean that your whole database fits in memory. You may have 15 years of historical data that's obviously not going to fit in main memory. But the data set that you use day to day that is really critical for the performance of your key apps can fit in memory usually fairly easily. So we're main memory optimizing this engine. So the in-memory OLTP system is optimized for the situation where the data stays in main memory. If we know that the data set for, say, a particular table is always going to be in memory, it's never going to be paged out, that means we can do things fundamentally different. You don't have to do I/O, but that's really a minor part of the difference here. You can buy a system with lots of memory with traditional tables, and they won't get paged out if there's no memory pressure. But we're taking advantage of the fact that we know that there's never going to be paging going on to do things fundamentally differently. So in-memory OLTP tables exist as the rows in memory. There's no page structures. Pages are just an artifact for moving sets of data in and out of memory. They're a convenient container for the data to get moved in and out. If we're not doing that, there's no reason to have pages. So if you've ever gotten hit with page latch contention where you're loading a whole flood of data with multi-threaded load program, and your primary key is something like a time series where you're constantly landing on the same page, you're experiencing a lot of page latching. Well, there's no page latching here because there's no pages. There's a whole lot of infrastructure within the SQL engine that is dedicated to understanding what data is resident in the buffer pool, where in the buffer pool, because it's different every time it loads in, and if it's not, where is it on disk, and if I need to bring something into memory, is there room for it? Who do I kick out to make room for this new data? All of that processing goes away. It makes things a whole lot leaner. Indexes get very interesting if you know that you're just in memory, right? Because instead of being logical lookups to surrogate keys within the index structures, these are just memory pointers. We have 2 styles of indexes within the in-memory OLTP. There's a modified B tree, which exists using memory pointers instead of logical references, but it also is carefully constructed so as to be lock-free, and I'll get into that later. The other class of index, if you're doing point lookups, is a hash index. So in a hash index, you define an array of bucket pointers. All the key values get hashed into one of those buckets. So when you go to look it up, you put the key value into the same hash function. It takes you to one of those buckets, which is a pointer to the row in memory. It's an order of 1 lookup. That's way faster than the typical find the base of the B tree, go to the next page, the next page, the next page, and that takes you to the leaf page, which has the data in it. Each of those steps, you have to crack the page structure, get down to your slot in the slot array, and decode that. None of that happens. Each of these steps just takes you to a row in memory. So it's way faster. Although the data is kept in memory, it is fully persistent. When we update one of these rows, it gets logged in the same transaction log that everybody else uses. That's the most performance-critical I/O in an in-memory database. Because you can have a mix of in-memory tables and traditional tables in the same database, they have to be logged in the same log structure to make a coherent update track record. We take the records out of the transaction log and persist them in a set of sequential files, stream-based file storage. So it's a pure sequential write pattern, which is really efficient. So we do very efficient I/O for the I/O that we do. So that's kind of the outcome of the observation that we can keep the performance-critical data in memory all the time. But how do we make more use of those CPU cycles that we have? Okay, we're using a lot of cores in parallel, getting that execution going in parallel really well. How do we make most use of those CPU cycles? So since we know where all the data structures are, and they're all in memory, we have gone the next step, and you can now define a stored procedure to be natively compiled, which means we'll take the T-SQL for your stored procedure at definition time, run it through the standard T-SQL optimization, and then convert it into C code, which gets run through the Visual C compiler and optimizer, and create a DLL that gets loaded into the engine, in the engine space. The outcome of all that is when you run one of these stored procedures, instead of being a collection of T-SQL statements that get run in as interpreted statements one by one, running a natively compiled procedure is just a function call at engine context. There's not even a context swap. Again, way faster, way more efficient, way leaner. The code paths just get way shorter. The amount of work that the engine has to do to satisfy the queries to get the business results that actually matter to you guys. You don't care about all the stuff that we do behind the scenes other than it's taking time that I don't want to spend. So we're doing everything we can to do less of that. So we're running your queries at native code speed. Another observation that we made is that all the commercial database systems, the SQL, outside of the NoSQL world, do a lot of work to make sure that you never have conflicts in your updates, right? Make sure that there's never any logical conflicts happening. In reality, it's really rare to have one of those conflicts. It's really rare to have two threads updating the same row at the same time. It happens, but it's rare in most workloads. So if we make that assertion and are able to handle the concurrency by way of using multi-version optimistic concurrency, we can get things a lot more efficient in that case. So instead of having the pessimistic concurrency model, which says, if you touch this row, I'm going to lock it and make sure nobody else can touch that row until you're done with it, and everybody else is just going to have to wait, because they might be changing it in a way that would be incompatible, and when you're done with it, then we'll let go and the next guy in line gets it. All those guys in line are just sitting on a lock wait. So you're burning CPU cycles, not making progress. What we do instead is we have a multi-version. So when you update a row in the in-memory tables, we just create a new version of the row in memory. The semantics are a lot like snapshot isolation, except we're not keeping a version store in tempdb. It's just a new version of the row in memory. And when no transactions that were accessing the old version of the row are still active, we just reclaim the memory. So that's how we get read consistency. For write consistency, there's one of the fields in the metadata on the row in memory is the timestamp when it was last updated. And so when a thread of execution reads a row, we note the timestamp that it read the row, that the row had when it was read. If they go to update it and the timestamp on the row in memory is different, then we know somebody else got in and changed it between the time you read it and the time you went to write it, so your update fails. It's the last updater fails. Again, there are some pathological scenarios where it really is a problem, and there's no way around locking, but those are really rare. Most systems get by really well with this scenario. So what does that buy us? This is how we get really highly concurrent systems running. So this is where you don't have any threads just sitting there idling, waiting for somebody to have access to the row. You can make progress on all those threads at the same time and make use of all those cores you're paying that good money for. Once one of these transactions starts, it's going to run to completion. Completion may be commit, completion might be rollback, but it's going to run to completion because there's nothing to stop it. It's not going to get thrown off for an I/O. It's not going to have any context switches. It's going to run through. So again, that shortens the time that each transaction takes dramatically, which again reduces the chance for conflicts. So this is how all the structures, I made reference to the B-tree style indexes being lock-free. They're actually architected in such a way that they use multi-version within the index structures and are able to do live updates with no blocking and still maintaining full consistency within the index B-trees. And the final pillar, which I think is a real differentiator and is really core to the way we think about this stuff, is that it's just SQL Server. It's built into the engine. If you install SQL 2014, SQL 2016, with Enterprise Edition, you get in-memory OLTP. It's just part of the product. Use the same management tools, use the same T-SQL coding surface area. In some cases, you can just change the table definition, reload it, and the same code can access it unchanged. Backup and restore just works. Always on high availability just works. You don't have to learn a whole new tool set. And the other thing is that because the granularity here is a table, it's not a database. So you define a table-by-table basis which tables you're going to put in memory. That means, one, you can make much more efficient use of your memory because you're not dedicating expensive DRAM to data that hasn't changed in the last decade. But it also means that you can be much more targeted about your approach. Instead of having to do a forklift upgrade, rewrite your whole application, all your data, now you can do some performance studies. This is not a substitute for understanding where your bottlenecks are and doing good testing. But when you do your testing, understand where your bottlenecks are, find what tables are really hot, and we do provide tools that will help you with that. Then you can convert the hottest table to in-memory. If there's stored procedures that are eligible, you can convert those too. Run the benchmark. If you have achieved the level of performance you're targeting, you're done. There's no reason to invest more work in it. If that uncovers another bottleneck that's painful, then you attack that one. So you can do it an iterative approach and a very targeted, and control your investment in this upgrade. So instead of being forced to upgrade the entire application, the entire database, now you can do it in a very targeted fashion. So at this point, are there any questions? Yes?
You mentioned that you do logging.
Yes, we do logging.
Then you said no write any logging. Is that just the optimization?
So you have, I need to qualify that statement. The statement is, we log all the updates for an in-memory table. And the qualification is, if you want to. So there's some very specific scenarios where you want all the rich query semantics of a full database, you want all the consistency guarantees, all the security protections, but the data doesn't have long-term value. So what am I talking about? What scenario is that? Think about an ETL stream where you pull data in from a fire hose to a midpoint. As long as the original source doesn't go away, you do transformations at that midpoint, and then you load it off into a data warehouse someplace. Well, as long as the source hasn't gone away, that data doesn't have a lot of inherent value. And so if it went away, it wouldn't be a catastrophe. The other canonical example is an ASP session state cache. Right? It tracks the state of where you are in the website you're going to for each login, and it gets updated every time you see a page. But if the system were to go down and come back up, that data would have no value because everybody else would have to re-log in anyway. So for those sorts of scenarios, we give you the option of defining a table to be non-durable. In that case, we don't log anything, and we don't write anything to disk. So all the I/O overhead goes away, and those tables are blindingly fast. The team has actually come up with a reference implementation of the ASP session state cache, the .NET cache. It's up on CodePlex. It's freely available. It's been tested and blessed by the ASP team, the .NET team. So that's the example of that.
That can apply to even regular tables.
No, it cannot.
Some delayed logging, eventual consistency, those kind of things are properties of logging and remain when they.
So we don't give you the option of not logging a traditional table. Only in-memory tables have that option. Give you a bit of a diagram as to what this looks like in terms of the SQL Server engine. So here we have kind of the big boxes within the SQL Server process space. And the big white box represents the memory space of SQL Server. We've got your application talking to the TDS handler. That's all the networking handshake code that we use to talk to applications. From there, a transaction, if it hasn't been seen before, goes through the parser, the optimizer, and gets put in the query cache, the plan cache. If it's been seen before, we just reference it in the plan cache. Go through the T-SQL interpreter. So after it's been optimized, gone through the cache, we go through the T-SQL interpreter, which interprets each individual statement. Access methods is the layer that understands how to translate the structures that are on disk and in pages to the logical data that you guys care about. And finally, you have tables and indexes in buffer pool, which mirror the tables and indexes in the data files and the transaction log. So those are all the pieces of SQL Server that we know and love traditionally. With in-memory OLTP, we add another region of memory separate from the buffer pool, but within the same SQL Server memory space. So the same SQL memory handlers, allocators, all manage that space, but it's separate from the buffer pool space. And we add a separate file group for managing those checkpoint files, the files that maintain the deltas. It's a container or a series of containers for handling lots of files that we manage under the covers. So we move a couple of tables into the in-memory space. They disappear from the buffer pool. They're now in the in-memory space. The tables move across into the in-memory space. And the indexes disappear from the transaction log. What's up with that? One of the other optimizations we realized is that in order to bring one of these tables online, we have to pull all the data into memory, because that's how we operate on it. So when you're bringing up the database, we have to read all the data into memory. We're going to see every row. Since we're visiting every row in the table, it's much quicker to actually construct the indexes on the fly as we bring the database into memory than it would be to persist it out on disk and bring it back in. All the locations would have changed, and the indexes are all made of memory pointers anyway. So we don't do any logging of index operations, and we don't persist them in the on-disk storage. So again, if you've been held up with logging of huge index operations, that doesn't happen. And so this is just representing the fact that you can have a non-durable table where it exists in memory but nowhere else. So the idea here is that the schema is fully persisted. When you come back up, the table exists, it's just empty. So there's two methods you can use to access this data. One is called query interop, which goes through the T-SQL interpreter, and it's just ad hoc T-SQL. Any T-SQL you've got today will run through this pipeline, execute just fine. It's very highly compatible for surface area. You can do joins across other tables, no problem. You can join in-memory tables, traditional tables, all that works. So instead of going down into the access methods layer, you branch out into the Hackathon engine. The other way is if you're doing a natively compiled procedure, the first time we run it through the compiler, build the DLL. From then on, we just execute those functions. So one of the important things to understand from this is that bubble right there, that's where we get all of our benefit from performance standpoint. Real-world apps, we've seen a range from 2 times faster to 20 times faster, depending on how well suited the app is to take advantage of this technology. We didn't really change the upper layers of the network interactions, so the communications getting in and out of the database engine aren't any different for one of these transactions than they are for any other database transaction. We also have the same log latency than any other transaction has. However, we are a bit more efficient in what we log. So we tend to log a lower volume for in-memory OLTP transactions than we do in traditional transactions. So the kind of point of this is if you're building an application and thinking about this technology, the more time you spend in the database engine, the more of your logic that's pushed down into the database engine, the more gain you're going to get, because you're going to pay a tax going in and out of the engine, going through those, the TDS handler, the session management, all of that code is going to be the same time spent whether you're doing a single row insert or you're inserting a million rows. So you're just paying that overhead. So percentage-wise, the overhead gets way bigger if you're doing just a tiny amount of work. So the more you can amortize that expense of getting in and out of the engine over a much larger amount of work, the greater performance gain you get. So the applications you see with huge, 20 times faster, they're doing that. If you have a really chatty application, you'll get some benefit, but it's not going to be as dramatic as that. Important thing to think about. So what does this stuff look like? It looks like T-SQL. So if you're creating one of these tables, it looks like a create table, right? You have this extra memory optimized equals on. That's what tells the engine, okay, this is in-memory OLTP engine. That's how you specify the durability. Is it schema and data or schema only? This is a hash index. The bucket count, you specify the bucket count, so that's an indication of how much memory we should allocate for that array of pointers. And that's going to really be a function on the number of unique, distinct key values you expect to see for that index. The ideal would be about 2 times. If you're within a couple on an order of magnitude one way or the other, there's no acceptable difference. If you get extreme skew between your cardinality and the bucket count, then you're going to see some slowdown, because if you're loading a billion rows into a table with 20 buckets, there's going to be a lot of hash collisions, and we have to follow those chains to find the row you really meant. So that will slow things down. With 2016, you're able to modify those buckets. In 2014, you couldn't. You'd have to unload and reload the table. 2016, you can just alter the index and change the bucket count on the fly. And that's how you specify a non-clustered index, is how we specify the traditional B-tree indexes that have inherent ordering. That's an example of multi-column indexes. So all the indexes have to be specified with the table because they become part of the table structure. So it's not define the table and then create an index. It's define the table with its indexes, and if you want to add an index later, that's an alter table, because we actually have the continuation pointers for those chains of hash collisions are in each row structure. So in memory optimized tables are optimized for high throughput OLTP. So that's what they're there for. They're not necessarily there for bulk storage of huge quantities of data. That's coming in 2016. We will support LOBs, but the first iteration did not. We were very targeted in 2014, we think about that as kind of the first steps. We intentionally we targeted specific scenarios and did them completely. There are some other scenarios that we just knew we weren't addressing, and we get to in the next iteration, which is 2016. So there are some limitations built into 2014 that are being relieved here, and it's all about making sure that we got these scenarios nailed. Create procedure, DDL. Again, it looks like just another create procedure. Native compilation, that's how we specify that this is to be natively compiled at procedure creation time. We require native procs to specify the ownership and schema binding at creation time because, again, this is compiled code. We can't adjust on the fly, so we'll have to recompile it if any of those parameters change. By specifying the owner in advance, we can pre-calculate all the permission checks. The other new feature is that native procs are bounded by an atomic block, and that means that all the changes within that procedure will succeed or fail as a unit. You can't get halfway through and then roll back part of it and then continue on. So the whole procedure succeeds or fails as a unit. Session settings, isolation level, language, et cetera, are also set at compile time, which kind of makes sense. There's a limit to the isolation levels that we support within memory tables because we don't have locks. Literally, this engine has no locks and no latches. We didn't implement them. So if some of the isolation levels, like read committed, the semantics of properly implementing read committed say that you have to block in certain cases, and we don't do that. So we don't support read committed. We support all the isolation levels that don't require blocking. We actually looked into can we block selectively efficiently, and so far we haven't found, and Microsoft Research hasn't found a way to do that efficiently without taking down the overall performance to a point where we'd lose all the benefit. So, some results. What does this look like in the real world? So I kind of alluded to the fact that there are some applications that are better suited just in their structure to this. We've seen apps in the real world in production get 25 times faster performance. Those are apps that are really well suited, that dovetail into this technology really well. A web station state cache, where you can use non-durable tables, highly transactional, always single point lookups. Those are the sort of apps that get really stunning results. Apps with periodic updates, heavy random reads, maybe 10 times faster, so read heavy. Legacy applications where they aren't really changing, maybe 4 to 7 times faster. Very update heavy OLTP, maybe 2 times faster. We've been optimizing for TPCC benchmarks for 20 years in this product, and we've gotten pretty good at it. So we're not changing that bar a whole lot, but in real world workloads, we get a lot better. So again, an application that's going to work best for this technology is going to be one that's performance critical memory, data fits in memory. That's a core value. You can't page this data out. Locking or latching is causing stalls or blocking. You're going to get a lot of payback just from getting rid of that locking and latching. Applications OLTP-like, so relatively short-lived transactions, which limits the opportunity for collisions. high degree of concurrent transactions, so you'll benefit from the lack of locking latching. Stock trading, travel reservations, order processing, all of those are the sorts of applications that work really well. Migration is going to be simplified if a lot of your business logic is grouped into existing stored procedures. That means that you're doing more work in the engine, so you get more benefit from those stored proc executions, as long as it's not create proc, insert row, end. And also if your performance problems are isolated to a specific set of tables and stored procs, which is almost always the case in my experience. These are some of the production customers we saw. Had our common labs, the SQL infrastructure machines, so SQL servers, IT department, if you will, is always the first to put this product in production. So we've already got 6 different systems within the SQL infrastructure running 2016 in production today. So we identified some patterns. Shock absorber is what we call the case where you've got this flood of data coming in that has big spikes in it. And your traditional tables can maybe handle the steady state, but they can't handle the peaks of the spikes. So in the case of the event reporting database, they're taking this flood of events. Anytime there's any anomaly within the build and test systems, those fire events. And if something goes south, they get this big flood of events, and they couldn't handle that in the that they were sending it to, and they just lose data. They just threw it on the floor because that's all they could do. So what we do is we put a hackathon table there in front of the bulk storage, and that's easily able to handle those spikes of input data, and then it just drains them off at a steady state that can be sustained. So that's a shock absorber. bwin, anybody here heard of bwin? Any of our talks? So bwin is one of our kind of poster children. They're a really fun customer to work with. They're one of the world's largest online gambling sites. Performance is really important to these guys, right? They're the only company that's ever walked into my office and said, Kevin, I don't care what it costs. Make it go faster. I don't care, because the faster it goes, the more money I make. Think about the last 20 seconds of a World Cup match. Have any idea how many people want to place bets at that point? The more those bets these guys can take in, the more profit they make. It's really critical to their business. They were completely bottlenecked on their session state cache. Everything else had been scaled out. They'd scaled up the session state databases as large as they could, but they were capped out at about 15,000 transactions per second, and that was bottlenecking their whole operation. They turned that into a non-durable table and got up to 250,000 batches per second, just making that change, and actually reduced the size of their server farm. Saxo Bank is Reedscale, Baltic Breweries, OLTP. So these are global companies. SBI Liquidity is a currency trading market, foreign exchange. A lot of different companies getting good benefit, good results. What we're adding in 2016, again, I mentioned that 2014 was kind of the first steps. 2016 is dramatically broadening out the number of scenarios that we're lighting up with this technology by increasing the surface area. We're enhancing security of this. Again, lighting up more and more scenarios end-to-end and more platforms supported. And what I mean by that is that we currently have in-memory OLTP Hackathon is in a private preview in Azure DB today in the Sterling platform. So that's the high-end Azure DB platform. It's in private preview now. It'll be in public preview over the summer, and eventually it'll be GA. So that's why this technology matters across all the platforms. So today you can do it in production, on-premise, in infrastructure as a service, so Azure VMs, AWS VMs, and soon you'll be able to use this technology in SQL DB in Azure. So any questions on in-memory OLTP before I change gears?
So blob data is currently not supported.
What?
Blob data in the columns is currently not supported.
Blobs? Blob data in 2014 is not supported. In 2016, it will be. There's workarounds. What? Yes, we will. In fact, bwin emulated blobs in their session state cache because their cache property bag was bigger. So they just chunked it up into 8K chunks and strung them together. Yes?
Is there a significant difference in the current time of the database? Have a lot of time
In what time of the database?
recovery time?
Recovery time can be significant because you are reading all the data. So it depends on how much data you've got and how fast your I/O devices are. In general, in all the benchmarks I've seen, we're able to ingest data and format it into memory as fast as your I/O system can deliver it to us.
When does that occur?
At database startup. So if you've got failover clusters, that's in line with failover time, so you need to take that into account. If startup time is not a big issue for you, then you can get by with fairly low-performing storage. If it's really critical, you want to pay attention to that. So what's the conversion from memory to disk? Look at the amount of, if you aggregate all the rows, that's approximately what it'll take in memory. One more, and then I'm
Support for distributed transactions?
not.
I did a roadblock with that in 2014.
Right. So currently, we're not supporting distributed transactions, and that's because all of our consistency within the in-memory structures are based on timestamps, and we can't synchronize the timestamps across systems. It's a really thorny problem to get the consistency exactly right and not make any mistakes in that case. So until we can't get it right, we're not going to ship it. And I know that's a pain for a lot of people, but I'd rather give you pain up front than give you pain in the back end when you got wrong results. Okay, one more, and I really got to move on.
Is there any toolkit available to try and assess the benefit you get from moving an application? So you might be calling a production workload over 24 hours scenario.
So it's a way to predict what performance you've got. We have some tooling that's built into the product in 2014, and it's being enhanced in 2016 that will collect performance metrics on a running workload, and the workload can be running on 2008 or above. And this will give you a report that gives you kind of relative how much gain will I get by modifying different tables and how painful is the modification going to be. It flags schema elements that may or may not be supported. It's not an exact, you'll get 4.5 times faster, but it's kind of a relative guide. I'm going to move on to the in-memory data warehousing. I'll be available afterwards to talk pretty much as long as you want until we both get hungry. So, how many people have dealt with column stores? Wow, I get to teach all of you guys. This is awesome. Column stores apply to data warehouse workloads. So you're talking about vast amounts of data, huge amounts of data that is scanned broadly, and you're trying to move. Today, with a traditional table, you have to move terabytes of data in and out of your processor, and that's really painful. The chart over here is just illustrating that the size of data warehouses is getting dramatically bigger over time. As big data kicks in, people are just putting huge amounts of data, and this chart is already way out of date. New data is typically appended to fact tables. You're not modifying data in place in your typical data warehousing scenario. So this is kind of couching what this technology is optimized for. Just looking at the column store technology, and especially clustered column store, what we're doing is storing the data. We're physically organizing it by column rather than by row. The ordering is maintained across the row segments, so the 45th element in each of those column segments is the same row. That's how you string rows together. But it's not optimized for doing a lot of individual rows, as you can see. But if you're doing aggregation of all the price data, it's really fast because you just look at that column. That's kind of the gestalt of what column stores are about. We also, because especially if you're talking about a fact table where it's typically numerical data and within a fairly constrained range for each column. That sort of data compresses really, really well, especially if you can eliminate duplications. So if you say, I've got 1,000,000 rows that are all value 0. Okay, that's 1 0 a million times. You can do that sort of run length compression with this technology and get just astounding compression. That middle chart kind of tells the story, where the left bar is the size of a table with typical indexing. If you add page compression, that's the next bar over. With no indexing at all, just the raw data, that's the third bar, that's 5. With page compression, it gets a little bit smaller. A table with a column store index, so you have just the base table plus a column store index, is the next to the last bar. So that's already substantially less than the first table. And if you put all your data in a column store, so it's a clustered column store, the clustered store is the column store, you get the last bar. And there's no need to have separate indexes for doing aggregation queries, because inherently column stores are efficient at doing whatever columns you happen to be talking about. So what is this stuff about? So the data is stored as rows in a typical store. Now we're storing it as columns. You get much better compression, reduced I/O, because if you have a query that accesses maybe 10 of 100 columns in a wide fact table, you only pull those 10 columns into memory. So you get a whole lot less I/O. That's how you keep from putting terabytes through that CPU and burning it up. More data, more of your logical data, if you think about the entire set of data, fits in memory at the time, because you're fitting the data that you really care about in memory. So this example is what really made it click for me. So this is what a row store would look like. So you're inputting data. You've got rows of data, product key, store key, region key, quantity, sales amount. It's all numeric. Typical fact table. A real fact table would be much wider than this typically, but for the sake of an example. So the first thing we do is we partition these into row groups, just to have a unit that's convenient for us to work for. And row groups are 1,000,000 rows, give or take. And there's cases where we'll cut off a row group with less than that, but give or take, say 1,000,000 rows. A bunch of data. So we partition them into row groups. Now we split them by columns. We have segments within the row groups. Each row group segment is a physically separate container. So we can access it differentially within the database. Now we compress each row group. So again, they get different amounts of compression because it's different data sets in each row group. And some of them are highly compressible. So if you have one column that has 5 values across 1,000,000,000 rows, it's going to get compressed really well. Depending on the data type, the pattern of data in each row, it'll compress a different amount. But typically you get something like 90% compression. Now we access the data. This is where the magic happens, more of the magic. So we have a query that says select product key and the sum of the sales amount. So how much money do we make off of each product from sales table within a date range. So the first thing we do is we say, that query didn't touch any of those columns, right? Is there any reason for us to pull them into memory? Nope. So we rule those out immediately. So we're not going to touch any of those columns. That just cut in half the amount of data that we have to look at to satisfy this query. But now we look at the predicate where it says where order date key is greater than some value. We notice that the second row group doesn't have any values in that row. There's metadata within each row group that says what are the ranges of data that are within that row group. So now we can knock out the whole second row group. And typically that would be extended much further. So now you've just got this relatively tiny amount of data that you have to deal with to satisfy your query. That's where this stuff gets really efficient for aggregations. So again, you're looking for each product key and the sales amount. You're dealing with a much more tractable amount of data, much fewer bytes. With 2014, we added updatable column stores. So not only do we have all this technology in place, which originally shipped in 2012, in 2012 it was a non-clustered index and it was not updatable, which was really painful. Because in order to update your data, you have to drop the column store index, update your data, and then rebuild the column store index. Not a great story. So we made it updatable in 2014. And the way that works is new rows that arrive end up in a row store. We stage them in a row store. If you query the table, we do a join across the row store and the column store. And again, the number of rows in that row store are bounded because it's going to be less than the size of a row group, right? So it's fewer rows in that row group. We can tentatively add those into the query. When we get enough to cap off a row group, we have a component, somebody named the tuple mover, moves rows across into a new row group, which then gets processed and compressed and just becomes another row group within the column store.
When does that occur?
It occurs when you accumulate 1 million rows, or if you're doing bulk load, we'll make the whole bulk load operation a distinct row group. So there's a few different scenarios that will govern when we cut off a row group, but it's somewhat dynamic, yeah. You can also force it in a number of ways. So insert values always land in the delta store, the row group up at the top. We don't, if you delete a row from a column store, we just have a bit map off on the side, and we mark that row as dead. So we don't go modifying these things after they're created. You can do a rebuild to reclaim that data if you've had a lot of churn, so you've got a lot of logically dead space, reclaim the space. But again, there's no locking, there's no big upheaval when you delete one of these rows. Modifying a row in a row store is a logical delete followed by insertion of the new value up in the row store. Again, it's not a big upheaval. And the model here is that for most data warehouses, you're not doing much modification. So a little bit about column store in SQL Server 2016. And again, there'll be other sessions that focus exclusively on this for the whole time. This is just a teaser. So functionally, we have fast equality search. So we're adding the ability to have a non-clustered B-tree index off on the side of a column store. So you have a column store as your clustered store. Now you can have a B-tree index that can efficiently find a single row within that column store, or short ranges. We enable that technology then allows you to have foreign key constraints, primary key, foreign key constraints enforced on a column store, which was something you couldn't do before. Again, it's broadening out the scenarios. There are some operations that would lock a whole row group. We're making all of those operations much finer grained in the amount of data that they lock. Improved supportability, full support for Mars, multiple active result sets, a lot of entity framework, application development environments, as well as ISV apps are built using Mars, so that's an important compatibility issue. Performance and high availability, online index maintenance, so you can reorganize these indexes without having to take anything offline. There's internal batch operations, which are really efficient ways for dealing with a lot of data. We have that for sort, windowed aggregates, string predicate pushdown. We now support the SIMD instruction set in the Intel processors for doing vector processing against these, which again just makes it that much faster. A lot of these different technologies that are making the column store much faster than it ever was before. So kind of summary, we're moving towards seamless integration across the whole platform. So we have column store engine for data warehouse, memory optimized OLTP, and disk optimized the basic row store engine. And always on, backup restore, security administration deployment is seamless across all of those spaces. transactions, queries, and stored procedures work well, but there's some limitations which we're working on relieving release over release to make them seamless. Some technologies that are applicable to just some of the technologies, but not others. Readable secondaries actually are opening up in SQL Server 2016. Range and column secondary indexes were limited to, actually those are still not in the in-memory OLTP engine. And there's some that are specific to an individual technology. Again, this is moving. This slide was created before 2016 was announced. So blobs are moving into the in-memory OLTP engine. And I'm not sure that they're getting into the column store. Batch operators are unique to the data warehouse just by their nature. Natively compiled procedures are unique to in-memory OLTP because of the nature of that technology. So that's not likely to change. So the point here is our goal, our drive within the engineering, as you can see from the progression between this slide and what's in 2016, is to make things seamless across the whole engine. It's, again, the whole move towards it's just SQL. You know SQL, you know this stuff. So that's a whirlwind tour through in-memory technology. There's a lot more coming in deeper dives. Here's the roadmap for it. Sunil has operational analytics this afternoon, followed up by in-memory OLTP for 2016. Column store index is Wednesday, so you can see a lot of different sessions coming up. At this point, I'll take questions until they kick me off, and then we can take it outside.